Okay. I'm going to give you a lot of information today, but you're going to have to be involved in it. And I'm going to ask a bunch of questions, and I hope you have some of the answers. But you've all looked at a globe like this, hanging at 22.5 degrees. But have you ever looked at it this way? What don't you see? North Pole, that's right. What else? Land. There's very little land in the southern hemisphere. Pretty amazing. Take away Antarctica and there's very little. Look where it all is. It's all in the northern hemisphere. Pretty dominant, isn't it? So if you look at it that way, then that means that the people live in the northern hemisphere. The vegetation's in the northern hemisphere. The pollution's in the northern hemisphere. Anything to do with land is all in the north. Now if I take my hand and put it over Boulder, Colorado here and bring it down, now relative to the size of this globe, how thick is the world's atmosphere? Okay, let's say 98% of the world's atmosphere. Stop me. Relative to this globe, if I was going to put an atmosphere here, a picture, how deep would it be? Right. There's two people know exactly. As thick as one of my gray hair. Can you believe that? When you fly in an aircraft at 30,000 feet, about 85 to 95% of the world's air is beneath you. At 18,000 feet, where you can drive to in a few places in the world, if not you can walk there, in Tibet maybe, half the world's air is beneath you by mass. There's a few molecules up here, but they don't count. So the atmosphere is very, very, very thin. It's so thin that a piece of paper or saran wrap or my gray hair would depict the total world's depth of atmosphere. Now, how deep is the deepest ocean? Same scale. Not even. You're right. The depth of the ocean is just about as thick as the atmosphere, or a little bit thinner. So all of the life that goes on in a small portion of that depth, because we grow our rice in the first meter, the wheat in the first 1.5 meters or meter, the corn in the first 2 meters, and in the ocean, most of the productivities in the first few tens of meters. So you have this incredibly thin life layer on the earth and on the ocean in an incredibly thin layer. Just think about that. Everything that's going on, all the gas exchanges, all of the production of food from the sun is all occurring in about 6 meters near the surface. Just keep that in the back of your mind, because that's where we also live. Now, if you burn 1 gallon of gasoline in your car, and we all burnt a few of those getting here today, how many pounds of carbon dioxide did you put into the atmosphere? Every one of you know. You really do. You just don't know you know. Okay, so how much does a gallon weigh? 5 to 8. You know, let's just, doesn't matter if you're out a few pounds, but let's say 8 pounds. Now you burn that 8 pounds, how many pounds of carbon dioxide go in the atmosphere?
24.
See, here's a man who's done his homework. He says 24. How can that be? Simple. You take this long chain hydrocarbon, which is made out of carbon and hydrogen, and for each of the hydrogens you clip off, you put a couple oxygen molecules. So you're taking and you're making CO2. You know, in carburetors, when you put your hand on an old engine, there's a lot of air going into the engine. Why is that air going in there? It's bringing in oxygen so that it can convert the fuel and make CO2 out the tailpipe. So you put in, you fill your gas tank full, how many pounds of CO2 do you put out, roughly? So you put in, what, 15 gallons? Multiply that by 8, multiply that by 3, it starts to get big. You're talking 300-400 pounds of CO2. So every tank of gas, every 2 tanks of gas is half a ton of carbon dioxide. Now think about that. Think about all of the oil that's being burned, all of the coal, all of the wood, all the natural gas. Think of all those tankers, the big pipelines. Pipelines nowadays are 3 to 4 feet across, and they're running wide open, full of oil or natural gas. That's all goes into the atmosphere. Okay, so what? Well, you got a thin atmosphere, and where does the CO2 go? Nope. Nope. Yeah, part of it goes in the ocean. The rest stays there. Probably half of all of the fossil fuel we've burnt, or maybe a bit less, is still in the atmosphere. And we're going to burn it all, aren't we? So we're changing the atmosphere. So okay, who cares? Well, a few people do, and the basic physics of this whole operation are very simple. The atmosphere is heated from below, not from above. The sun comes through the atmosphere, hits the earth, and then heats the earth, which radiates up and heats the atmosphere. Now, half of you don't believe me, but why do you go up to Estes Park in the summer to be cool? It's closer to the sun. It should be warmer, shouldn't it? But it isn't. It's cooler because you're going up a little bit. You're getting away from the heating of the earth from below. So as you go up in the atmosphere, it gets cold very quickly because you're being heated from below. How does the atmosphere warm up? If sunlight can come zipping through it and not warm it up, how can it be warmed up? Well, the long wave radiation from the ground goes up and it gets caught in the atmosphere. And there's a number of things that catch it, but one thing that's important is carbon dioxide. A molecule of carbon dioxide is like a feather in a feather bed. If you have a thin blanket on a cold night that's an inch thick of feathers, you have a certain heat, and that you're heated because your body is heating it and the feathers in the feather bed are catching it. So if you took and doubled the number of feathers in that feather bed, you'd get warmer, wouldn't you? Or triple it, make it a 6-inch feather bed. You're going to get nice and warm because you're heating the blanket from inside. It's exactly how the atmosphere does. Each little carbon dioxide molecule acts like a feather in a feather bed. So the more you put into this blanket, this thin blanket that covers the earth, the more heat it's going to hold. And that's the basic physics. Now there are other things that do this too. If you look upon carbon dioxide molecule as being a big rough goose feather, methane is like the finest eider down you can get. It holds more heat. So we're putting out carbon dioxide, which is heating it. We're putting up methane, which is changing it. We're putting up nitrous oxide. Those are the 3 big ones. And there are a lot of little ones. But basically, we're changing the composition of the atmosphere. And we're changing it on a basis that we can measure over the space of a few days to a week. We can see these changes going on. And I'll show you some of that. But there are a lot of other chemicals that are going out into the atmosphere. Everything that we evaporate. When you paint a wall, your paint's wet and in an hour it's dry. Where does that stuff go that was keeping it liquid? It's in the atmosphere. It doesn't just blow away to somewhere else. It stays in the atmosphere, it goes into the ocean. Now, if I ask most people in the world, populated, which direction does the wind blow on average? What would they tell me? The developed countries. West to east, right. So you go to the US, the wind blows from west to east. You go to Europe, blows from west to east. You go to Russia, China, west to east. Now, you put something up in the atmosphere, how long does it take to come back to you west to east? How much? That's a very good number. 3 weeks. Let's just use that. It might be 4, it might be 2.5, but you got the point. So, China puts up something. How long does it take to get to Hawaii? Anywhere from 2 days to a week. Depends on how fast the winds are blowing. The point being that we all live in somebody else's sewer. The U.S. puts their stuff up, we put it up, it goes to the east. Remember when the Denver brown cloud used to be strong, and people would say, oh, we're going to get a good wind. It blows away. All of a sudden, the clouds went to Kansas. Well, of course. But then from Kansas goes somewhere else. Europe goes somewhere. It goes around. So keep that in mind. When you go to Hawaii and you look up at from one of the beaches and you see a kind of a light, it's not exactly clear blue, it's just a little bit hazy up there. That's the pollution from China. Hawaii is very polluted. It has more dust storms and more pollution events than New Mexico or Arizona coming from China. And I'll show you one or two of these. Okay, I just set this stage for you to show you what is going on in the basics of the world. Now, a lot of people might argue that climate change is not happening, or if it is, it's natural. I'm not going to argue anything here. I'm just going to show you the basic physics of what goes on. And that's the agency that I work with. That's what we do. We measure the world's air. And if you can envision this globe as a patient in a hospital, we measure eyesight, breathing rate, heart rate, blood pressure, weight, nutrition, all around the world. And we do this from many places. And as it's changing, we present that data, and you're going to see some of it today. And then we use that, we don't use that, I should say, other people use that to make policy and or rules for how we should all use our resources and not change the atmosphere. You've all seen this title, or you probably wouldn't be here. That tune is the air we breathe. It ain't what it used to be. It's the same as the old gray mare. She ain't what she used to be. That's the tune. Now, this is some stuff that you should put in the back of your mind as we go here. Each person roughly eats 2,400 calories per day. But the average US and Canadian uses 100 times more than that. The energy. We use that energy for this lighting, for transport, for food acquisition. So where, well, this is it. Driving, cooling, cooking, you name it. We use it, that energy. It's like having 100 serfs, 100 people working 24 hours a day, 7 days a week. For each of us, have 100 people working for us, making energy, burning food, cooking stuff. And they all have energy needs too. Oh, sorry. And all of these calories, about the 240,000 that each of us use every day, come from what? Oil, coal, and natural gas. And in burning those, of course, it goes into the atmosphere. And we here in the US and Canada use about 4 times as much per capita as Asia does. But the Asian economies are growing, and growing much faster each year than ours. So eventually, can you imagine if all of the Asian people, how many, 1.x billion in China and as many in India, if they waste and use as much energy as we do, what's going to happen? The price of energy is going to go up, the atmosphere is going to change fast. Not that they're not allowed to do that, because we've been doing that for 100 years. Why can't they? Swan and I went to China when it first opened in the early 80s, and we've been going back to China regularly. The first time we went, nobody had refrigerators, or very, very few. Nobody air conditioning. What are you talking about? What is air conditioning? Private cars were almost non-existent. Since the 80s until now, it's a complete change. People we know now, you go there, they have houses that are nicer and bigger than ours. Marble floors, double refrigerators. I know a guy that I've known for 30 years, a Chinese scientist. When I first knew him, he lived in a little apartment. They shared a kitchen with other people. Now he's got about a 2,000 square foot apartment, big double refrigerators, but he can't drive a car. But he owns a beautiful BMW, big BMW. And I asked him why. He said, very simple, I can afford it, I like it, and on weekends I get a driver and I say drive 3 hours that way. And he says, I just look and I enjoy it, I turn around and come back, because he can do it. He's never had that freedom and that choice. Same thing we do. We've all got cars. Can you imagine, as these economies grow, how much more the cost of oil and gas is going to be as they use more of it. But anyway, I digress. This is the organization I work for, and we monitor, as I said, the world's atmosphere. We have 7 global networks. I'm just showing you one here. This is the network for gas sampling. At these big squares are where we have permanent stations and people living, and I'll show you a little more. Where the red darts are, each week somebody goes out and fills 2 bottles of air very carefully and sends them back to us. And then we look inside those bottles, and we can look for hundreds of things. Now let's give you an illustration. If I collected your garbage every week, but you didn't know I was collecting it, and then I put it in this big hanger and spread it all out and studied it, in a couple of years I'd know an awful lot about your life, wouldn't I? I'd know your income, what you eat, you name it, your medicines. That's exactly what the atmosphere is like. All the chemical processes, all of the industrial processes, all the commercial processes leave an imprint, and they go into the atmosphere, and some of those imprints are changing. Now, you'll see where we have these, I guess they're kind of stars, the NATO star. That's where we have light aircraft that every week go up and sample in the vertical. And where these green triangles are is where we have very tall towers. You know, like the Erie Tower out east here, we have access to about 11 of those where we have them instrumented. So we can see the 3-dimensional picture, because most measurements are done at a couple meters above the ground. But what's really of interest also is what's happening above. So you've got to understand that. The red circles are ships at sea. These are ships. This is a ship that we used to do this line, and it was off for about a year, but now it's back running again. So these ships go, and every 5 degrees they take samples, and then like we put bottles on in LA and take them off in Christchurch, and then the same here. It goes from Wellington to Japan. So it's coming down, bringing Toyota cars to New Zealand and taking lamb and sheep back. And these things go every 2 weeks, a week this way, a week this way. And we're sampling on them every 5 degrees. Here's some of the more permanent stations. Manalo Observatory has been in operation since 1956. There's 11 people work there. That's at 11,000 feet above sea level. It doesn't look like it, but it is. This is on the largest mountain by mass in the world. This is one of our more exotic stations, South Pole, Antarctica, right on the pole, except the pole is, the ice is moving, so the pole is over here now somewhere. Eventually this station in a million years will be in the ocean. Cape Matutula, American Samoa, Point Barrow, Alaska, Trinidad Head, California, and Summit, Greenland. This is just one of our sampling pieces of equipment. The whole station is much bigger, but we just put that in because we're kind of proud of that. The snow up there, it snows about 2 meters a year, so every couple of years you have to raise this up. It's one of the snowiest places in the world. It's hard to believe that. And working at one of these stations is quite an experience. The people that we have are generally young, very energetic, and a little bit strange, because to live at South Pole, isolated for a year, takes a very special person. And we have one staff who's on his 13th year there. He doesn't have a life anywhere else. He's got lots of money because he doesn't spend any. He's a fantastic engineer, but he gets out for a couple of months each summer, Antarctic summer, and then he goes back, and that's his life. He's an amazing person. But at Greenland is actually harder than South Pole because it's so cold up there, and you have to work outside. And this is people putting up a balloon. It's minus 60 C. This is dark, and these lights, it's a time lapse. That's why it's a little blurred. But they go out and put up balloons. See this package? That's a package of instruments that measure ozone and temperature and pressure. And then this is the balloon. And this balloon, when it blows, will be about 150 feet across. It'll go up very, very high, and as it does, the pressure is less, so it just keeps expanding. Then it explodes, and then it comes back down on this parachute. We don't recover these in Antarctica ever, unfortunately. But they do this in the winter, sometimes 3 times a week, and that's hard. So in Antarctic or in Greenland, they only go for 3 months, and then we send a little plane in to pick them up. You're thinking, gosh, this is expensive. Yes, this operation is incredibly expensive. Thank you, taxpayers. The tall towers, this is what they look like. This is one in Wisconsin. It's in the middle of a forest. It's 1,000 feet tall. And then we have sampling at different levels. Light aircraft. We used to have 19 of these. Now we're back to 9 due to budget cuts. But within those, there's little containers, suitcases that have bottles in them. And these bottles are very clean. And there's a pump system. And when the pilot loads this in, there's a little readout on the dash that says, "Good morning, pilot. Please fly to X, Y, and Z." And he gets up to wherever that is. And all of a sudden, a light comes on and says, "Press button 2." And he presses it, takes a sample, says, "Thank you, that sample is good. Go to," and then we give him another place to go, and he goes and gets there, same thing. So we can send out these all around the world, and we have light aircraft contracted, and we all have, the planes have a little inlet that we give them either in the window or the wing. So we can send out a package in the afternoon on FedEx, and it'll get to, let's talk about the U.S. The next morning, the pilot picks it up. He flies. He puts it back in FedEx that evening. We get it the next morning. So we can do a sample in the U.S. and get it back in less than 3 days. Around the world, if we're doing, say, Mongolia, it takes about 6 days or 5 days to get a sample there. So we can sample a lot of places in the world very quickly. And these bottles come back, and this is a different style of bottle. Remember I said that people collect them at all of these other red dotted sites? Well, these are the type of bottles they collect. They collect them in pairs. They're about 1.5 feet, 2 feet long, and they collect them in pairs and then send them back every 2 weeks, every week. And they come back, and these, it takes about a week to learn how to fill a bottle of air. We bring people in and train them because they can be contaminated. If you breathe anywhere within probably 30 feet of the sample when it starts, and we sample them with a little automated box and put them in and press a button and run away. Or if you cough, or if you use some kind of aftershave lotion, and it even gets anywhere near the sample, we can pick that up. We can pick up something 1 part per trillion. Now, do you know what that is? Let me give you an illustration. I had some senators come once to talk, and it's hard to get their attention. So I collect gold coins. So I had a bunch of gold coins, and I stacked them up on the ground, and of course they started looking, and you could see them, how much is that worth, you know? And I said, okay, if you take those gold coins and stack them from my feet to the top of my head and make a wall this wide. What's that measurement, by the way?
2 meters.
There's another nautical measurement.
Oh.
Fathom. Right.
Oh.
That's how you measure rope depth. You pull it out, it's 1 length, 2 length, and that's a fathom. So you make a pile of coins, silver dollar size, a fathom by a fathom, and you run it 200 miles. So that would be from here to northern to Custer's Last Stand in northern Wyoming. So you make a wall 6 by 6 by 200 miles. That has 1 trillion coins in it. You take one of those coins anywhere in there and scratch it. We'll tell you where that coin was taken from. You bring it back to us, and we'll say that was 182 miles, 6 feet, 2 inches, and you scratch it. We'll tell you what side you scratched it on, and we'll do that 99 times out of 100. That's the accuracy of our measurements. So keep that in the back of your mind. That's why we bring the bottles here to measure, because you couldn't do it in the field with that accuracy. And the reason we can do that is we make the standards for all of the measurements. NOAA here in Boulder is the world standard for carbon dioxide, methane, nitrous oxide, all the halocarbons, carbon monoxide. We are about 10 times better than the Bureau standards. The Bureau standards buys their standards for these gases from us. And we have 7,000 tanks like this in our building, coming and going and being calibrated. And you see these tanks laid level here? The reason for that is that if you put a tank like this, it could be 1/10 of a degree different at the bottom than the top in a room, and that was enough to change the whole calibration. So you lay the tank level, then you put your sampling line right in the middle, right there, so it's always at that height, and you keep the room absolutely the same temperature, then you're fairly sure that your calibration is good. For every data point we make 2 calibrations. We make about 1 million measurements a day. So you can imagine how much of this gas that we're using. Our biggest expense is making and maintaining calibration gases. Anyway, these flasks come in, they're logged in automatically with a barcode, and then they're analyzed. Usually we do 8 species on them, but we can do up to 120. Depends on how much we're interested in something. And these are done for years and years at the same location by the same people. And in Mongolia, there's just a small interesting story. We sample, there's a school teacher samples, and she walks 2 miles carrying this backpack and all these bottles out to a hill to do the sampling. And it has to be done on a Tuesday morning around 10 o'clock. The whole world does it that way. And she got sick once. So her husband went and did the sampling. And she was sick for a while, so it was -30 or something. So he thought, oh, this is craziness. Why don't I just go out and fill a whole couple months worth of bottles, and then we'll just send them in. Well, he doesn't know that we put in a tracer in the gas, in the bottles, that is not in the atmosphere. And when we look at the bottles, we can tell 2 things. If they flush them enough, and secondly, we know in that part of the world roughly what some of the species, tracer species, should be. And we picked that up immediately. And they were just amazed that we could say, on this 2 months, you went and did them all on this day. So from now on, they all come good. How many of these do we do a year? About 20,000 are in motion all the time. And now finally to some data. This is carbon dioxide. Here's years across here. I don't know why that's there, but let's not worry about it. Pick a year. Most of us were born down in here somewhere. And here's the concentration of carbon dioxide. Okay, pick the year you were and look across, and you can see it's going up and up and up. And it's not a straight line, is it? A straight line would go like this. Why is it getting faster and faster? Because we're burning more and more fossil fuels. We're getting richer, there's more people burning, so you can see the increase. Now, what is this little up and down sawtooth pattern each year on that? This is Mauna Loa, Hawaii. There's the average, but what is this up and down? Summer and winter, exactly. In the spring, vegetation sucks out the CO2, because vegetation grows on what? What are the components that make vegetation? CO2 and water. That's all that vegetation grows on. You plant an orange tree in a pot, weigh the soil, weigh the seed and everything, and then start adding water, and eventually harvest oranges, and then you get rid of the tree, weigh the ground. The ground weighs the same or it's even more. That oranges and all the trees came out of the atmosphere, nowhere else. Didn't come out of the soil, came out of the atmosphere because of the water and the CO2. So each spring, think of all of the forests, the corn, the wheat growing, sucks up that CO2 and down it goes. And then in the fall, vegetation shuts off, but we're always burning a little fossil fuel, so each year we get a little tick, a little increase. Tick, 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 tick. Keeps adding up. Now remember, back to this globe, all the vegetation's in the northern hemisphere, isn't it? And all the population. So you should be thinking, well, was the carbon dioxide and the annual cycle larger in the northern hemisphere? It should be, shouldn't it? Because that's where the vegetation is. And that's exactly what you'll see here, that it's very dominated by the northern hemisphere. But first, let's look at this animation. This is the equator, this is the South Pole, this is the North Pole, and this is CO2, and this is by month, by years. Now what you can see here is that the northern hemisphere puts out CO2 and takes it down, and then the CO2 mixes. But see, by the time it gets to the South Pole, how it's just kind of gently rising. And we'll just keep going through this for a while. The red dots are measurements over land. The blue are over sea. See how the oceans don't take up and put out CO2, whereas the red dots on land do? But the point to take home on this is see how this whole average blue curve is going up. And this stops in 2000 something. We haven't updated it. But if we go to today's, it'll be up here at the 400s. And that's probably going to continue. And it's the same for methane and for other gases. But this is, I call this the skipping rope. You can just see though how it just keeps going up. But it's all in the north that's driving this whole process. Here's 1996, 97, 98. See how CO2 is going up? 2000, 2001, 2002, 2003. I think it stops at 4, doesn't it? 5. Oh, it's even there. And that's all due to man and the burning of fossil fuels. How do we know that? We can look at the carbon dioxide molecule and we can tell where it comes from. We can tell if it comes from burning of wood, coal, or oil, because they all have different signatures in them. Now, if you take and freeze frame all of the CO2 measurements, this is year across here. Okay, it's going this way. This is the equator right here, northern hemisphere, southern hemisphere. So if you come up straight, the equator is right there. And here's the north. See how the Earth inhales in the spring and exhales in the fall in the northern hemisphere? The equator is right across here. That's because of all of the vegetation and all of the people living up here. And so the Earth is breathing on a regular basis. Inhales in the spring, exhales in the fall. But it's much stronger in the northern hemisphere than the south. You see that? And it's dramatic. And the color as it goes from green to red is the increase in the CO2. And you can do this with many different gases. I'm just showing you one in the interests of time. But now let's look at another gas, methane. Remember I said methane is a stronger radiation gas than carbon dioxide. So what is methane doing? Well, for years when I first started in this business, it was going up constantly at about 10 to 12 parts per billion. And then it started slowing down, and then it stopped and actually decreased a little bit. It went up and down, and now it's starting to go up again. And you might be asking, well, this is nothing like CO2. This is very different. Yes, it is. Because what are the sources of methane? Animals a little bit. Anaerobic decomposition, like decomposition of vegetation underwater that occurs in rice paddies, occurs in flooded Amazon. But also, one of the biggest sources is leaky pipelines. Natural gas is methane. 4 to 10% of all of the natural gas that's being dug out is lost to the atmosphere. So for years, leaky pipelines were probably one of the main contributors to this. And here is the growth rate per year. So it's fairly steady, and then it goes up, and then it really goes down. Now we've studied this right here. What political event do you think might have influenced the methane concentrations to be very high up till about 91 and then just to stop? A political event, major political event. Okay, let me back up and give you some information. Which country in the world produces the most oil? No. No. Russia. Russia. Well, now it's maybe it's lost it, but it, until for many years, produced and sold the most oil. Think about that. Number 2, which country produces and sells the most natural gas and ships it? Russia. Hey, Russia, a pretty big player here, eh? What happened in 1991? Right. What happened when the communism fell apart? No, something even simpler than that. In the Russian economy, you didn't really count like when you put methane in at the wellhead, because the only place it really counted is when you sold it to Germany. So at the German border, you would measure it and then sell it to Germany or whoever. After communism, little companies started to form. There was companies that did the drilling, company that did the transporting, and company did the selling. All of a sudden, what they were putting in at the Siberian fields was a lot less than was coming out in Germany. Why? That's one thing, but they killed a lot of people for that. But what was the other thing? They were leaking. The pipelines were leaking. Nobody knew or cared. They hired a company from Idaho. There's a big company up there, construction company, world side. Anyway, they went over, fixed the pipelines, and look what happened to the methane. Almost to zero. The leaky pipelines were losing billions of dollars a year. Now the U.S. pipelines we're finding are doing the same. We just did a study in Utah this winter, and when we publish that, it's going to be kind of surprising how much methane they're losing in the system. Anyway, this is one we've studied. We looked at the isotopes of the methane, and we could tell it was coming from, a lot of them was coming from the Siberian oil fields. But up it goes again. What happened here politically in the late 90s in Russia? Remember the devaluation of the ruble by a factor of 10, not 10%, 10? They couldn't fix their pipelines. Sorry, their pipelines were leaking again, and boom, up it went. They fixed it. So little things like that can change the whole atmosphere. There's still a little bit of question about this one here, but now methane is starting to go up again. And these are the Arctic measurements. And these are not coming from the pipelines. We know that because we can look at the isotopes. So people are thinking maybe the permafrost is starting to melt. The permafrost in the Arctic has more carbon than all of the natural gas and oil fields in the world. It's all frozen. If that carbon starts oxidizing, either anaerobically or otherwise, you're going to get a lot of CO2 or methane. So people are quite concerned. So we've put up some new stations in the Arctic to monitor this. But that's not where it's coming from. Surprisingly, everybody thought, oh, well, of course, it looks like it's really coming from the Amazon. And the reason for that is that it's been much wetter for a few years in the Amazon, so the water is higher, a lot of vegetation under the water, and it's decomposing. So sometimes things that look one way on the surface are quite different. How do we know it's not coming from the Arctic? Well, we put up a bunch of stations up there. Well, not a bunch, 3 or 4. This one is right in the permafrost at Chersky, Russia. And you can hardly see it, but there's a tank there, a Russian tank that floats across Muskeg. So with our cooperator, we got this building and hauled it about 40 kilometers out into the Muskeg. There's no roads up there, of course, and there's no buildings. And then we got a tower, stuck it up, and we put in our instruments and insulate them really thick. And the heat from the instruments keeps this nice and warm, even minus 30 or 40 in winter. And then we have a generator about 12 kilometers away over here on a river, and the people keep that generator running, and we got this long power line hanging laying across the tundra. And we're measuring methane, and we don't see any increases there. And we're doing this in 3 different places. But this shows you how you can do research fairly quickly with using local resources. This didn't cost us much to set up, and the Russian charges very little to operate. To get there takes you about 6 days from here, because you have to fly to Moscow, then you have to fly to Chersky, and then you have to, in the winter, take a truck up the river for about 60 miles, or in the summer you take a boat, and then you trundle across over to the site. Takes you another half day or so to get there. But we only have to go there once every year or two, and it's well maintained. That's been operating continuously since 2008. Now, let's look at animations of the carbon dioxide in the atmosphere. This is something called Carbon Tracker. If you take all of the data that we have on the carbon dioxide concentrations in the atmosphere on these dates, you can see where the equator is right here. And all of this action, the red is higher concentrations, the blue is low concentrations. So all of the low concentrations are in the southern hemisphere until we go into the spring. And then see in the spring and summer how all the vegetation just sucks out the CO2. Now you say, why is there a lot of CO2 down here? Because in Africa there's huge fires. The Sahel is burnt and the forest is burnt each summer. So there's a lot of CO2. The red is high CO2. You can see a lot of it coming out of here, but a lot of it's coming out from the high Arctic where people you think don't live, but what's happening is it's moving up there and collecting in the Arctic. Now you watch when we get into June and July. See how the CO2 goes from very high concentrations to very low because it's being sucked out. And then when you get into the fall, you watch this will go kind of neutral. It's still August, September, things are still growing in the forests really well. September it's starting to get cool. By October, frosts are coming on pretty heavy. Vegetation shuts off. We go into a neutral state. And now the burning of fossil fuels, see the US here and see China, places over here, are putting CO2 above the average level. And see in winter, it doesn't really peak out until February when in the coldest. See, look at China here, just streaming out. But the US also, and Europe. But see, the Europe goes up north. Now, in about, let's say late April, early May, you're going to start seeing that vegetation is waking up. The reds are not as bright. Look here, they're starting to suck the CO2 out in June, and then they really kick in June and July. And you saw all of that both on the visualizing on the globe and then in the data. Now, let's have a different story. That's the carbon cycle and methane story. You've all heard of ozone depletion and the Antarctic ozone hole. Are you aware that the Antarctic ozone hole only occurs for 90 days each year, and it only occurs right around the perimeter of this? You just draw a line around Antarctica, and it only occurs inside that line. And it only occurs when the atmosphere is colder than minus 80 C, the ozone hole. That chemical reaction that doesn't make sense, does it? Chemical reactions are supposed to work faster when it's hotter, but there's two things going on. Around Antarctica in winter, you get the air flowing around, and it forms a boundary, and within that boundary, air from the southern hemisphere can't get through that vortex. It's like a wall. So you have this big cauldron where the chemicals, HFCs and chemicals that destroy ozone, collect in the dark. And in the summer, when the sun finally comes, it's like throwing a match into a big open tank of gas. Within 10 or 15 days, all of the chemicals that have collected in the dark are ignited, and they eat the ozone up, just like that. And then the ozone is gone for a month or two, and then when the sun gets high enough, this vortex breaks down, fills it in, and the ozone hole's gone. So the ozone hole starts late September, early October. It's finished at the end of December, early January. So it's an annual thing. Now, it's a good thing it happened down here because there's no people. Sunlight comes in at low angles, so that it doesn't really affect you. But if this ozone destruction occurs at higher latitudes, especially where people live, then you're going to have a lot of problems. And 2 years ago, not this winter, but the winter before, we had a mini ozone hole over the Arctic. The Arctic is much warmer than the Antarctic, and you need to get the temperature cold enough in the atmosphere to make something, make a nitric acid flake. And you get these flakes of nitric acid that form at cold temperatures. Then the fluorocarbons or the ozone destroying chemicals sit on these flakes, and that's the substrate, and then the chemistry can work on that. And that's why it only works when the air gets cold enough to make the nitric acid snowflakes. And the Arctic is really quite warm because the Arctic is floating ice. And if it's floating, it means it's on water. If it means it's on water, it means the temperature of the water is what? Right, just at freezing. So you have a lot of cracks in the ice. So you have this heating coming up all winter long in the Arctic. So it doesn't get very cold here. You know, the Eskimos in the early days used to build their snow houses on the ice. Why? Right, they have a furnace in the basement, the heat coming up. They never heated those things. You'd ever wonder how a person could live in one of these? The heat would collect. They have the thick insulation. They might have a little oil lamp, but that's all. And they were semi-undressed because it was so hot in there. You build an igloo over a ground, you freeze to death. You build it over ice, you have a furnace down there putting out a lot of heat. Free. Now, again, another digression. Let's talk about this. When the ozone hole was identified in the 1980s, they very quickly found out that it was produced by chemicals called fluorocarbons, or HFCs. So the Montreal Protocol was brought in what year? 91. We were measuring these gases before that, but you'll notice here that the concentrations of HFC 11 were going up very fast, and then after the Montreal Protocol, look how fast it came down. Look, methylchloroform. These are the four that are controlled. Methylchloroform went down really fast. Carbon tet, up and then down. But CFC 12 did not. Why? You all know the answer. That's one thing. Number two, how many refrigerators do you have? How often do you buy a new refrigerator? Not very often, 2 or 3 times in your life. There's a lot of old refrigerators, and when you sell them in Boulder, you sell them, a student buys them, puts beer in them. Because if you turn them up high, when they have very little HFC in them, they just don't freeze, but the beer stays perfect. So for another 20 years, you're pumping out these HFCs. So the Montreal Protocol worked beautifully. Look what happened, but CFC 12 is going to take a longer time to come down. So the ozone hole problem should go away in the next 20, 30 years. And we're almost finished now, but we still have refrigeration and air conditioning, of course, so the chemicals that were put out to replace those are all going up. Everything we produce, and we even replace something, goes up. These aren't very bad for the atmosphere. They're much less problem, but some of them are greenhouse gases. So this one here, HFC 141b, it was replaced the CFC, or methylchloroform, or one of the CFCs. It was going, and then it was controlled here in 2002, and it started going down right away, and then all of a sudden, boom, it kicked up again. Boom. This one did the same thing. It didn't even get down. How was that? Developing countries are not they have about 10 more years before they have to control it, and they found out that it's better to produce this and smuggle it into the US and sell it, because you can get more money than you can for cocaine. Because a lot of you people have an old air conditioner in your car, you'd much rather go to a store and say, could you just put some of the old stuff in? Okay, saves you $300. Now, put this all together. What have we done to the atmosphere? Here's years across here, and this is the radiative forcing. This is how much energy extra the atmosphere has captured. If we go to 1990 and set it at 1 and go here to 209, we have increased the energy capacity of the atmosphere about 30%. And that energy's got to go somewhere. It's either going into the oceans or the atmosphere. So eventually we're going to have climate change. It may not be hitting us too hard now, but you can't stop it because you've increased all of this energy in the atmosphere. Okay, dust from China. Here's a satellite picture. Here's a dust front. Korea, Japan. See how this dust, every few months or every few weeks you get these storms. They push out pollution. In front of it, see the pollution here? Behind, the air should look like that. If any of you have ever been in Beijing, at times you can see it gets very polluted. The fronts come through. It's beautiful. You know that there's ski hills near Beijing and mountains with snow on them. You don't see them very often, but after this all flushes out, you see it, and then 2 days later you don't. This is like all of the pollution collects, fills up, and you flush it, boom. Where does it go? Well, here's a distance of 2,000 kilometers. In 2 days, it goes that distance. It goes to Hawaii. Here's samples taken at Manalo Observatory. And these are timed, 24-hour samples, and the time progression is 1, 2, and 3. So when the first, I'm sorry, the other way around. In front of the dust, you get all of the pollution. It all looks black. And then when the front gets closer and you get the mixture of dust and pollution, it looks this. And then when you get it right in the dust, it looks like that. And these things just pump by, boom, 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 boom. This stuff continues on to the US and around the world. We do the same thing. But it's just that we get good pictures from the Pacific. That's why I see this. You could do the same thing through Atlantic. The Chinese or the Asian mainland flushes their toilet about once every 7 days to the atmosphere. You know, get the picture. It builds up, and every 7 days, flush, flush, flush. So these things are just going around. And now, here's something, another country that's starting to really come up economically. Here's India. This is a satellite photograph. Here's the Himalayan mountains, Tibet, the Ganges River. But you see this yellow stuff? Haze here is pollution, and pollution runs just like water. Cold air flows just like water. So if you look at this picture, this was just, again, kind of a biased picture. I could find that it was a clear day in the morning in the winter in India. But you can see how the pollution is flowing out into the ocean here. And that's the same thing that happens in all continents, but it's particularly visible here. In winter, the air comes down from the Tibetan Plateau. The winter monsoon blows this way. In summer monsoon, all this goes up, deposits on there, and it's starting to melt the glaciers, where about 1/5 of the total world's population gets its water for food is in these glaciers here. From China, India, Bangladesh, all get their water from these glaciers. As they're melting faster, you can imagine the potential problems there. Now, something home. The U.S. consumes much, much more oil than it produces. There's a big gap here. This in 2007, it produced 20.7 million barrels per day, or used, but only produced 8.5. There's this gap. Where does this gap come from? Canada is the biggest supplier of oil to the U.S. Saudi Arabia second, Mexico third, Nigeria fourth, Venezuela. Then you get down to Iran, Iraq. Iran doesn't even show up in here. The little bit of disruption in the Iran oil fields is affecting the oil. Can you imagine what happens if Venezuela has a revolution, or Nigeria, or Canada decides to sell to China instead of the U.S.? You remember that big pipeline controversy you've heard about? They stopped. Well, China is offering to build a pipeline from the same oil fields to the west coast and to take every gallon of oil that Alberta can produce. All of this, it basically is coming from the oil sands in Alberta. Of course, that's why they're very rich up there. That's where I come from. I made a big mistake moving away. Now, kind of in summary, historically, you can look at ice core bubbles and see what the concentrations of carbon dioxide, methane, and nitrous oxide, these are the three big greenhouse gases. Nothing much changed until here. What happened in about 16, about the middle 1700s? Industrial Revolution, burning coal and stuff. And boom, look at how the concentrations are going up. And that's year 2000. Now they're up here, and they're going to be up here in 10 years. So we are changing the composition of the atmosphere, which is changing the radiation balance. What is it going to do to us? Modelers say that it's going to get hot. Anything above a blue color is where modelers say it's going to get hot. Basically, most of the world's going to get hot, except south of Greenland in the North Atlantic. And the reason for that is that's where you have cold seawater bubbling up. So it's not going to be hot there. But everywhere else, so it's going to get hot. What's that going to do? Well, two things. It's probably going to raise precipitation in Alaska up here, but it's going to reduce it in the southwest U.S. and Mexico. A lot of other places, but let's just talk where it concerns us. So what's the big deal? This is the bottom line. Food source. The global temperature change and the yield change. We're going to cut down. Asian rice is not going to be too bad, but we're really going to cut down on U.S. corn, Indian wheat, and African corn. And you only have to cut, you're talking 20 to 40% reduction in these basic food. All our cattle eat their corn and we get our meat from the corn down here. And corn is one of the biggest producers in the U.S. There's a huge production of corn, both for eating, but mostly for animal food. So those are some of the projected issues of climate change. And with that, I thank you very much for hanging in here. And any questions you want, I'll answer. Politically, social, financial, doesn't matter.
For your whole career, do you feel pretty pessimistic about the way the world's going?
Nah, I'm pretty optimistic. We've gone through lots. I mean, think of what it must have been like during the middle of World War II when people were dying by the millions and the world economy was all in chaos. We managed that. We control our environment pretty well. Most of us here have ancestors that came from Asia or Europe in a completely different climate zone. If we can just control the population, then we can survive. But population, if you have a population growth that's 3 to 4% a year, or even half of that, your economy has to go that much or more just to stay in the same place. By doing that, you have to consume more, and you have to burn more energy. And all these things are finite, and also we're affecting the atmosphere. But for the most part, at least rich countries like ours, we're going to complain a lot. Oh gosh, gas is up 6 cents this month. But we can afford it. But it's the countries on the marginal zones that are going to be affected the most. And if we could help them with population control and basics, that way would be much. But overall, we're going to survive. We just might be in a little different form. We just won't be as rich as we are, maybe. And we won't live in a 3,000 square foot house. We'll live in a 1,500 square foot house. But we'll survive and move on. It's just that we dislike change. And we always like things to be improving if things don't quite improve. And we should be reducing our consumption, you know. Sir?
You talked about you don't see much effect of climate change yet. Do you think climate change will be manifested gradually, or will have a case of punctuated equilibrium where we're going to have sudden dramatic change?
I think we're going to have, well, we already are in climate change. It's just most of us don't want to face it, but the glaciers are going back. The Arctic ice cap each year, you know, the Arctic ice cap is an annual event. It reduces in the summer and then expands in winter. It's reducing more. So there are a lot of changes. But there's some evidence, strong evidence, that we could have catastrophic shifts in climate, especially in the Atlantic. The Atlantic conveyor belt can switch off in just a few years. So I would say at some point we're going to have something like that somewhere. We just don't know. We're playing with a system that is so delicately balanced that the world's survival in many ways is balanced on it, and all it has to do is change a little bit and it could go. And that has happened in the past. And people predict it might.
You mean the distant geological past?
Yeah. The last big one was about 10,000 years ago, the really big one. And then there was the little ice age in the 1600s. So yes, the climate can change. It can just shift gears. But we are not very good at predicting that yet. Keep paying your taxes, and we'll keep trying.
Anything about the contribution of landfills to the amount of methane?
Yeah, landfills on methane, it's probably very small compared to the overall picture. It has a local effect, but really we only use a very, very small percent of our land with landfill, and what we put in does put methane, but a lot of landfills now are recovering the methane. So it's a small picture compared to the combustion and the oil drilling and stuff like that.
Is anybody measuring that?
Yes, EPA requires that. And we've done some measuring out east. We're going to do again next month. We're going to do all of eastern Colorado and see where the oil fields, the landfills, the power plants, and we're going to do a whole inventory. Sir?
At some point, maybe in a few hundred years, we'll have burned up all the carbon available. What will happen then? Will the temperature reach its maximum?
Yeah, the question is, once we burn up all the fossil fuels and carbon, it'll stabilize, but it'll be an effect probably for 1,000 years. If we shut off all carbon dioxide output today, we wouldn't see the effects for 100 years, and it'll still be around for 1,000 because it stays up there. And as it stays up there, even if you're not adding more, what you've already put there is still adding a lot more energy to the atmosphere. So the concern and why people say we should be reducing it now is to slow this effect down so it won't be so bad years from now.
And you didn't mention possible effects of methane hydrides in the ocean and warming of the oceans. And whether that could be a...
This gentleman is talking about a very interesting phenomenon at the lower parts of the ocean, especially in cold oceans. Methane goes into a clathrate or a hydrate. It makes an ice, and there's a lot of it in the world, and it has a lot of methane. And then if you reduce the pressure or warm it, it can come out. That's probably going to happen later after we've melted the permafrost. The permafrost is right near the surface. But yes, there's all kinds of scenarios of bad things that can happen. I didn't mention. We're only talking, but there are a lot of good things too. But yes, hydrates, clathrates are an issue. But again, these things generally aren't quite as bad as the worst projections, as you've seen. But I can't really predict accurately. I just guess. So leave it back here.
CO2 stays in the atmosphere for 1,000 years?
Some of it does.
Where does it go?
It goes away. It goes into the oceans. Slowly, the oceans suck it up, and then it goes eventually into carbonates. But the oceans can't take too much more right now because they're getting saturated. It takes a long time to remove it. And you've heard of acidification in the ocean. The CO2 is going in, changing the pH, which is now changing how shellfish make their shells. So there's a lot of interrelated. It's like a big waterbed with 3 or 4 people laying on there. Somebody rolls over or gets off, and everybody else is affected. And it's the same thing. Sir?
So as you raise the temperature of the atmosphere, it can hold more water. Is that what's causing the big extremes in?
Yeah, this gentleman brought up something I avoided because we really don't know what's going on with moisture. As the atmosphere warms up, you get more moisture, you get more clouds. That can change the whole equation because warm moisture holds more energy. So there's a lot of people starting to work on that. But for years, people said, well, there's always been moisture in clouds. Let's just look at CO2 and methane. But the clouds are something very important, and there's a lot of work going on that. And I'd say in the next 10 years, we'll understand that. There's a huge lab in the Arctic at Barrow, Alaska, just looking at Arctic clouds. There's another one in Indonesia looking at tropical clouds. And you're talking hundreds of measurements, hundreds of people just trying to figure that out. Sir?
Volcanic activity puts dust in the atmosphere, and it's been shown that that can reduce global temperatures a little bit. So I guess I'm just wondering what % of what you guys measure includes that volcanic?
When I prepared this talk, I was going to show that, but I thought it would get too long. Volcanoes can cut about 15% of the energy coming to the Earth for a short time period, for days, weeks, months, or maybe a year or two. But it's not a long-term solution. Other people are saying, well, we could put sulfuric acid all up there and coal the Earth. You can, but it's going to be pretty expensive. Why not just cut down population a little bit in our use? But volcanoes, yes, in short terms, they can really cool the atmosphere because it reflects energy away. And there was a period in the 15 or 1600s when all of the masters' paintings in Europe had these beautiful sunsets in it. And people thought all these guys were smoking pot or something, because there are no sunsets like that in Europe, especially Northern Europe. Beautiful reds and yellows and greens. That was actually from a volcano, and it was there. Krakatoa blew up and put all this stuff up for 5 or 10 years. All the artists saw it and painted it, and then of course it fell out. But that could happen again. And we have a line of stations from the Arctic to the South Pole looking with laser beams all day long to detect when that happens. What we're going to do about it, who knows? But that's not my responsibility. I got an easy job here. Sir?
Well, I'm an organic farmer, and so the soil's hot, and we have lost a lot of our forests, in this country, 90%. And as your graph shows, they sequester this carbon. So I'm just wondering if mass deforestation has a policy issue, like, reduce slope and stuff.
Yeah, forestation, yes, it's important. Would reforestation help bring the CO2 down or control it? Yes, it will. The problem, though, is it's like a bank account that's only got a lifetime of 60 years or something, or 100. Either the forests are harvested or burned. So if you increase your forests for 50 years or so, you're going to be sucking the CO2 out, but then they're either going to burn or be otherwise decomposed. So yes, it's a very good policy in the short term until we can get other ones in, but it's not the long-term answer.
But there's also succession forests and even grasslands.
Yeah, if you could keep it. But our population growth, we lose it because you're in Africa and South America, you cut the forests so that you can grow more cattle to grow more beef to eat, and a lot of in this country. But the forests, if there's a chance of a person maintaining a beautiful big tree or cutting it down and becoming a rich man and feeding his family for a year, the tree's going to go. And that's what happens.
I have I got some news about some opposite things about the climate change as a kind of some politician, even some scientists saying that it's kind of, politics, plot something
Yeah.
So what do you think about it?
He's mentioning about the climate change skeptics. It's good to have skeptics because it makes us a little more honest. But the big picture is that if we don't have a lot of climate change now, just wait 10 years or 20, because you can't argue with the basic physics of the atmosphere. It's the same thing like the housing bubble. Remember when everybody said, well, buy the biggest house you can, because we all know that it's going to be worth more a little while later. So and this whole thing went up, and nobody believed that house prices in Boulder would fall 15%. No way. But they did. It's the same thing that's happening with this climate issue. We're in the point where everybody says, well, or some people say, man can't be affecting this and nothing has happened. But just wait. Realities will hit in. And the realities are the physics of the atmosphere. You cannot argue against that. Politically, you can say mankind is not affecting it. You can say climate has changed a lot in the past, which it has. But at the moment, mankind is changing it dramatically. Just wait. If it's not here now, it's coming, because you can't argue with basic physics.